So welcome everyone. Welcome to today's session, and I welcome you all. Today's session is going to be extremely important. The reason being because the lecture is very simple. It is a straightforward lecture, but you need to keep some things in mind, some formulas in mind, which we will mention. And these questions will be asked in 5 marks. So directly the 5 mark question will come. In last many years, any paper you pick up, there is one 5 mark question definitely there, and sometimes one 5 mark question is there and one 3.5 mark question is also there. So one or two questions you will find in an exam because this topic overlaps with solid state physics as well as with statistical mechanics. Hence this topic becomes very important and simple to understand, but you need numerical, not as such mathematical, but algebraic calculation little bit, or you can say some dependencies on mass, and so these things we will discuss in detail. Okay, so the topic is quantum statistical mechanics. Now when we say quantum statistical mechanics, one thing that you have to understand is that we are either talking about bosons or we are talking about fermions. Everyone know what is boson, everyone know what is fermion. So when you are dealing with fermion, you have to deal with Fermi Dirac statistical mechanics. When you are dealing with bosons, you have to do with Bose Einstein statistical mechanics, right? So these are the two statistical mechanics you have to deal with. So we will cover one by one both of them, right? We will not understand that how does bosons behave, how does fermions behave. Neither we will understand that what is behind these mathematical bars. Right now our target is to do the revision, and so that which makes us capable of solving the problems rather than understanding the concepts in depth. So we are not understanding concepts at this moment, but enough I will tell you so that you have some understanding of what is going on. At least this much information you must have. So let's begin. So number one is Fermi statistical mechanics. So let's begin with this. Give me the three examples of fermions, three Fermi particles. Three examples. Yes, you can type or you can unmute. Yeah, three examples. Yeah, everyone. Electron, proton, neutron. Okay, good. Any one more other than electron, neutron,
Graviton.
proton? Yeah,
Graviton.
graviton is a fermion. You sure?
Muon
It's
towns.
boson, boson.
Graviton is a boson. Yeah. Muon is a good example.
Neon, neutrino.
Neutrinos are good example. Pions, yeah, yeah. ठीक है, all of these are the examples of fermions. Okay, and we just basically need to deal with them. Okay, so let's begin. So in Fermi statistical mechanics, number one thing that they will ask you is what is density of states. Okay, so density of states basically is number of states available between energy E and energy G. So let's understand, let's give you a picture. So let's say you have a system. Okay, so for this point of view, we will always understand with the infinite well. So because infinite well is very simple to understand. So we have infinite well. So let's say you have infinite well and you have many energy levels, 1, 2, 3, 4, 5, so on, infinite energy levels. Okay, so this is your system, and now in this system you are putting your Fermi particles. Let's say in this box you are putting electrons, right? So now first question I can ask is, what is density of states? Density of state means that how many states are available between energy E and energy E plus dE. In a small energy, how many states are available? Because states are quantum, they are discrete. One state is here, one state is here, one state is here, one state is here, so on. So I can ask you that in this energy range between energy E and energy E plus dE, how many states exist? That is something we call it as density of states. Okay, so GE into dE, okay, multiplying dE tells you that how many states are there between energy E and energy E plus dE. And if I'm only looking at GE, it basically tells you that how many energy, but basically how many states are there around this energy level E, basically. Okay? So simple idea. So our density of states depends upon E to power d by s minus 1. So that is the first formula you all will write in your notebook. Density of states depend upon energy E to power d by s minus 1. Minus 1 is also in the power. Okay. Now we have to please note this down first formula, and then now we have to understand that what is d and what is s. D is the dimension. So if you are in 2D, 3D, 1D, depending upon that, you can even the question has came from 4D. So what is a dimension? That is basically D. What is S? S comes from dispersion relation. Dispersion relation means kind of system you are dealing with. Every system, so let's say I have one dimensional well, I have free particle, I have black body radiation, I have photon, or I can say I have muon particle moving, massless particle moving freely, or I am in crystal, I am in BCC lattice. All of these are different systems. So what changes from one system to another? It dimension is not dependent upon system. It is basically dependent upon in how many dimensions you are working with. So what actually changes from one system to another is dispersion relation. How does your omega depends upon K, or how does your energy depends upon K? E is the energy, or even omega can be understood as energy. More the omega, more is the energy. So E and omega are energy factors, or you can say frequency factor. How does they depend upon K? K tells you momentum, or you can say wavelength. Okay. So you must have heard this thing that momentum space. So this basically tells you about momentum space, and this basically tells you about energy space. Okay. So how does your energy depends upon K? Without going into much detail, dispersion relation is a relation between omega and K, or energy and K. In some questions it will be omega K, in some cases it will be energy K. Does not matter. So if energy is depending upon K square, then S is 2. If energy is depending upon K, then S is 1, and so on. So this first point is clear to everyone. Yes. Number 1 point. Yes, this formula. We're not going in too much depth, but yes, everyone clear. So you should be knowing that from one system to another, dispersion relation changes, dimension we have to keep in mind, and now density of states. What is density of states in general, and how does they depend upon energy? Okay, all of this is clear. Next step. Sorry. Next step. Second step is, now this was about the system. This information has nothing to do with fermions, right? This was about systems, that in my system, how does density of states changes with energy? So if I am at a lower energy, my density of states will be something else. If I'm at high energy, my density of states will be something else, because my density of states are depending upon energy. This was all about that in which dimension you are working, what kind of system do you have, all of that. There was nothing about first point which was specific to fermions. That you have to understand. Density of states, basically this first point is universal. Now second, Fermi statistics. Now we are adding Fermi particles in our system. So system we defined, now we will put Fermi particles. When we put Fermi particles, then the Fermi statistics will be applicable. In the same system, you can also put bosons. Then the Bose Einstein system will get activated. Right? But in first case, we are putting Fermi particles in our system. So when you put Fermi particles, according to Fermi statistics, there is something known as Fe. Small f into E. This is a parameter which gets defined. Fe tells you that what is the probability that your particle can occupy the energy level E. Okay. So basically what I'm telling you is that in your system, you have one energy level at E. Okay. So what does GE into DE tells you? At energy level E, let's say energy level E 2 electron volt, at 2 electron volt, this is the density of states. Okay. That is what the system has. This is like a building. You have a building in which at energy level E, this is your density of states. So basically there are this many states are available. So these are the available states. in the building, the rooms are available. Fermi statistics tells you that when you try to put the electrons, let's say you try to put the fermions in this, what is the probability that these fermions will occupy these states? What is the probability that fermions will occupy the energy level E? Okay, because these electrons has many options. They have a ground states also, first excited state also, many options are there. So we need to understand that what is the probability that my electron will actually go and occupy this energy level E. Okay, so that is the understanding here. So in general, that formula is given by this. That this formula is given by this. In general, so it is given by 1 by 1 plus exponential E is the energy, EF is the Fermi energy by KT. K you know is a Boltzmann constant, T you know is a temperature. But we don't need general formula. You can note it down, but we don't need general formula. Our entire calculations will be at low temperatures. All the numericals, everything. Even if it is not given, you assume low temperature. Okay? So low temperatures. In low temperature, this formula becomes very simple. This formula becomes 1. So your probability is 1, basically 100%. If your energy is less than Fermi energy, and it is 0 if your energy is greater than Fermi energy. Technically, this is true at 0 Kelvin, but this can also be assumed as true at any low temperature. Well, this is approximately true at any low temperature. Okay? You don't have to worry about what is low temperature. You don't have to worry about what is the exact number of temperature low temperature means. All these things you don't have to worry about. Low temperature, basically your Fe becomes 1 if your energy is less than Fermi energy, and it is 0 if E is greater than Fermi energy. So here I will define what is Fermi energy. Fermi energy basically means it is the highest possible energy your system can have, your electrons can occupy. So basically this was your building. In this building there were many energy levels. So let's say this is your Fermi energy. So all your electrons will occupy the states which are less than this. So they will occupy the floor which is less than Fermi energy floor. So let's say Fermi energy floor is 7th floor. So all the electrons will be below 7th floor. No electron will be above 7th floor. So Fermi energy is the highest possible energy level which the electrons are occupying. There are even energy levels exist even beyond Fermi level, but electrons are not occupying that. Why electrons are not occupying? Because probability of electrons to occupy state which is more than Fermi energy is 0. There is no probability that electron can occupy an energy level beyond Fermi energy level. That is why no electron is occupying. So how do we define Fermi energy at low temperature? Because since we are dealing with low temperature, we need definition at low temperature. So at low temperature, the definition of Fermi energy is the highest energy level which any electron can occupy. So in your building, what is the highest floor your electrons can go and occupy? So I hope that you are now clear with density of states and what is Fe. Fe is the probability that your electron will occupy energy level E. And what is the formula we are going to use for low energy, low temperatures? Yes, is the point number 2 and point number 3 clear? What do you say, everyone? Any doubt here? Either is it clear or is there is a doubt? Yes, go on. So please note down this, okay? Note down this. You have to keep this in your notes, because when we will be using formula solving the questions, this formula you will be needing. Okay. Let's go for fourth point. Total number of particles. How do you find? Well, you know total number of particles. You usually know total number of particles. So let's say I give you that total number of electrons are 3 million. Okay. So tell me what will be the Fermi energy. I can ask you to tell me what is Fermi energy, or at least how do they both depend upon each other. Okay. If not exactly, then how does exactly both of them depend upon each other? That is what basically I can ask you. So for that purpose, the formula is very good. It is given by total number of particles equals to integration of f of E into GE into DE. So we need to understand this integration. So total number of particles basically means that your particles are occupying the states. Now your particle occupying the states will depend upon two things. Number one, how many states you have, density of states, right? This we call it as density of states. First of all, how many rooms do you have? And if you have so many rooms, then occupation will be different. If you have less rooms in your system, the occupation will be different. So number one parameter which depends upon is how many rooms do you have. Second thing which it depends upon is probability of occupation. Okay, you have these rooms, but what is the probability that I will occupy this room? If you multiply both of them, then you can find the total occupation, or you can say total number of particles occupying this building. Okay, so total number of particles is a multiplication of Fe into GeDE. GeDE tells you the density, number of states. Okay, and Fe tells you, Fe basically tells you what is the probability that I will occupy it. And if you do integration, all the energy levels are covered, because you need integration so that all the energies are covered and you get total number of particles. Right. So is this the meaning of this formula is clear? Yeah. What do you say?
Sir, hello, sir.
Yeah.
Sir, we are calculating number of particles not for a particular level, but for a particular range of energy level, right?
Total. This is a total number of particles. If I want particles in, so let's say, yes, if I'm saying that particles in energy E to E plus DE, I'm just saying that
Yes.
what are the how many number of particles are there between energy level E and E plus DE, means in this small region. So then I will say, okay, GE into DE, how many rooms I have in this energy band, multiply by what is the probability that you will occupy this. So this will be small number of particles in this range. If I want total number of particles, what I will do, integrate. Then this dn ka integration will become total number of particles. Yes, clear all
Basically,
of you?
sir, G of
Uh,
E should be the density of a state, and D is just a number of energy levels, or we can say energy is spread in a particular range, D range.
yes.
G is
D is a
the
density of states, and then multiplying by DE tells you that in this range how many particles are there.
how many levels are there? Okay.
Yes, clear to all of you. Everyone, please mention me in the chat box. Everyone clear with this formula?
हेलो
Yeah.
सर
जी स्नेहा बताइए.
सर एनर्जी सर एनर्जी
हम्म,
तो डिस्क्रीट होती है ना तो फिर डीई रेंज ऑफ एनर्जी से क्या मतलब हुआ
एनर्जी डिस्क्रीट होती है, बिल्कुल ठीक बात है. सो सी क्या होगा, when you have so many energy levels, you have so many energy levels are closely spaced, they are close to each other, hence summation is almost converted into integration, right? When you have like this, so they are almost like integration, perfect, right? So that is the thing. So ge into d का क्या देखो क्या होता है ना, this, let's understand this, let's understand this.
ओके सर
So what I'm saying is that let's say this is your system. ठीक है, let's say this is your system, the
यस सर
density of states. So let's say here the states are away from each other, here the states are little close to each other, here the states are even close to each other. So I need density of states at any, so let's say this is how my energy is increasing. So this is my low energy, let's say 0, this is my energy 1, this is my energy 2, this is my energy 3. I want density of states at energy 2, so I will find G2. Okay, if I'm writing something like GEDE means how many states are there between E and E plus DE, basically this range. ठीक है, how many number of states are available to you. ठीक है, perfectly fine
ओके सर ओके
है.
सर एक क्वेश्चन और था सर ये फर्मी एनर्जी की डेफिनेशन आपने लिखी हाईएस्ट पॉसिबल एनर्जी लेवल इन द सिस्टम एट द लो टेम्परेचर सर ये डेफिनेशन हाई टेम्परेचर पे नहीं होगी
So, आपकी आवाज बहुत स्लो है स्नेहा. यस.
सर आपने फर्मी एनर्जी की डेफिनेशन लिखी है It is the highest possible energy level in the system at
Occupied
the
by
low
electron. Yes,
temperature.
yes. We can change like this. Highest energy level occupied by
At the
electron.
low temperature.
Yeah, occupied at low
सर ये
temperature. Hmm.
ओके सर,
Yeah.
तो सर ये हाई टेम्परेचर पे सेम डेफिनेशन नहीं रहेगी?
नहीं रहेगी ना, मैं वही बोला, हमें हाई टेम्परेचर की डेफिनेशन बिल्कुल बदल जाती है. हाई टेम्परेचर स्टैटिस्टिकल मैकेनिक्स इज वेरी डिफरेंट. ठीक है, ओके, वो हम नहीं बात कर
ओके
रहे.
सर,
राइट नाउ वी आर
ओके सर,
नॉट टॉकिंग.
थैंक यू सर.
ठीक है, यस. एनी अदर डाउट क्लियर विद दिस? सो सिंपल, क्या आपको अभी एग्जाम से पहले आपको क्या माइंड में यू शुड कीप इन माइंड. देखो, total number of particles is a integration of Fe into Ge into De. GEDE tells you that how many states are available. System के पास how many rooms are available. Fe tells you that what is the probability that you will occupy that. That's all. Right. I only on two parameters things will depend upon. Either how many are there, and Fe is basically what is the probability. Okay. There is no need to rush too much. Okay. I know that exam is after 1 week. Don't worry. All the questions will get completed in 90 minutes. Okay. Even if someone has a doubt, we can clarify. Every minute if you will rush na, you will be in unnecessary anxiety. Don't worry about it. Okay. No one can teach you faster than I can. Don't worry. Okay. Sure. Okay. Let's move on from here. And now let's simplify this formula. What is Fe? What is the Fe that we are going to use at low temperatures? Fe is equals to 1 when energy is less than Fermi energy, and Fe is equals to 0 when energy is greater than Fermi energy. So what I will do is I will put Fe as 1, and now my limits are only from 0 to EF. So now my limits are only from 0 to EF. I cannot go beyond EF, because if I go beyond EF, Fe will be 0. Then this entire thing will be 0. Okay? This entire thing will be 0. However, if Fe is 1, Fe is 1 only from 0 to EF. So that is why your limits are from 0 to EF. So this formula basically simplifies into N is total number of particles equals to 0 to EF Ge into De. So that is your simplified formula. Please keep this in mind. Please note down this formula. Yeah. Please note down this. Yeah. So once you solve this out, okay. So how do we find the Ge? That I already told you, that Ge depends upon e to power d by s minus 1. So we know even Ge, we even know the formula. Once we put this Ge here, we will do the maths in the numericals. So ultimately what will happen is you will find the relation between total number of particles and Fermi energy. And we will do that. In the questions, we will be using this formula to find the relation between total number of particles and Fermi energy. Okay. So this is a point 4. Now comes point 5, which is known as average energy. One thing that I will tell you in from my experience or as such, average energy, ground state energy, energy of the system, anything such word is used, you always find average energy. In the quantum statistical mechanics questions, if they have given, if they are written ground state energy, or they have written average energy, or they have written energy of the system, in all of those cases, you usually use this formula of average energy only. But I'm not saying this as a universal fact. I'm saying that from the fact of quantum statistical mechanics questions only. And when we will do it, you will understand. Okay? So average energy formula changes very little bit. So whenever you have to find average, all you do is, so let's say I need to find an average of A. So I will multiply A here. If I have to find an average of energy, so I will multiply by energy here. That is why the average of energy is given by E into Ge into Fe into De. And the same treatment I will do again. I know that Fe is 1. Fe is 1 if I am from 0 to EF. And it is 0 otherwise. That is why Fe I am putting as 1. And my limits are now from 0 to EF. That is what you see here. So my formula simplifies to this. So is the point 5 clear to all? Yeah. Just one page formula, then questions we will start. Perfect. Let's go on. So now we will understand two different kind of systems which are very common. Number one kind of system is known as free system or infinite potential well system. Even in infinite potential well, you know that in an infinite potential well, potential inside is zero. Inside the well, potential is zero. Potential zero means force zero. Potential and force are closely related. If potential is zero, force is zero. Perfect. So if you here anytime free systems, free particle, and infinite potential well particle, in all of these cases, the particle is free. It is not experiencing any force. So if there is no potential, then only kinetic energy is there. And kinetic energy is given by p square by 2m. And you must know that from quantum mechanics, momentum is written by h by lambda. This is known as de Broglie's theorem. What I will do is I will divide by 2 pi and I will multiply by 2 pi. H by 2 pi is known as h bar. 2 pi by lambda is given by h cut k. 2 pi by lambda is wave number or k. And h by 2 pi is h bar. Hence, my momentum is equals to h bar k that I will put here. So I will get h cut square k square by 2m. Hence, I can say that my energy depends upon k square. So the value of S is 2. So my dispersion relation is e ki power k square, and hence my S becomes 2. This is my 2. Dimension will depend upon the question, what dimension they have given. So in case of free particles, my S is always going to be 2. Okay. There is one more case, massless particles. In case of massless particles, energy is simply going to be P into C, right? And how do we understand that? How many of you remember this formula? Do you all know, remember this formula? Yes. So if it is a massless particle, this goes to 0. So simply your energy becomes Pc. And what is P? I just talked h cut k. So in this case, energy is dependent upon k. So S is not 2, S is 1. S is not 2, S is 1. So which comes out to be, for massless particle, my dispersion relation is this and my S is going to be 1. The last formula that we need before the questions is pressure exerted. Whenever your particles are in some container, whenever your particles are in some volume, some area, they exert the pressure on the walls of the container, or maybe because of the interaction with each other. Mostly it is on the collisions with the walls of the container. So let's say your neutrons are inside the nucleus. So neutrons are exerting some kind of pressure on the walls of nucleus. How do we find that pressure? That formula is given by P equals to S by D plus S N. One thing I want to be very clear in this, in my questions, I will not worry about if I'm using N or capital N. N is known as number density and capital N is known as number of particles. Okay? Number density means total number of particles per unit volume. So the only difference between small n and capital N is the volume factor. Volume is a constant. Okay? So whenever I am finding the dependencies in my questions, I will not worry about that. I will anytime replace capital N with small n, because all I need to do is divide by volume and that will be perfect. So when you're dividing or multiplying with constant, dependencies does not change. How do you depend upon something will not change. Yes, it will just constant numbers will get multiplied. Okay? So in my numericals, and you also keep this in mind, I will anytime replace small n with capital N or capital N with small n. Your answers will not change with that. Okay? Chalo. So the pressure is given by S by D plus S small n into Fermi energy. Okay? This is an exact expression. In the questions, most of the times they will be asking you the dependencies. Okay? Chalo. So is all the 6 points clear? Yeah. Can we go on for questions? So okay, let's go on for the question. बोसॉन्स के लिए क्या फॉर्मूला होता है, वी विल टॉक भूमि. प्रेशर का फॉर्मूला मैं वहां पर भी दूंगा, ठीक है, डोंट वरी. लेट्स डू फर्स्ट क्वेश्चन. So please have your notebook ready, and it is like whoever answers the first kind of situation now we have. So we have a competition, open competition kind of situation. You have to learn also and apply also. So you will give the answer only when I ask you the answer. Okay. So the dispersion relation of electrons. So the moment I see electrons, it means I have to use Fermi Dirac statistics. Okay. Then I am in 3 dimensions. The moment I say it is in 3 dimension, D is 3. Okay. Fermi. So dispersion relation is given. E is directly proportional to K. So S is 1. ठीक है. Vf is a Fermi velocity, does not matter, it is just a constant. If at low temperature, so you are at low temperature, Fermi energy Ef depends upon number density. How does Ef depends upon number density? So how will I solve this question? So one question I will do for you. So how will you do? First of all, I need density of states. So density of states depend upon, so you see, I only need dependencies. I don't need anything else. So how does my Fermi energy depend upon number density? Number density or number of particles. As I already said, I will anytime replace n with capital N. So how does this thing depends on it? So density of states can be written as e ki power d by s minus 1. If you do that, you will get 3 minus 1, which is basically e square. So your density of states depend upon e square. Now I will use my formula, which is total number of particles equals to 0 to Fermi energy GE into DE. Okay. So GE is E square. Now I am only worrying about dependencies. So equal to becomes up depend upon into DE 0 to EF. Again, so if you do that, you get E cube by 3 0 to EF. ठीक है. So this becomes EF का cube. 3 को ignore कर दो because I am only looking for dependencies. So if you make 1 by 3 on both sides, so EF depends upon n to power 1 by 3. So which option will be correct for me? Option number A. Is this question clear to all of you? Yes. So this is your formula number 1. Point number 1. This was your point number 4, which we used in our notes. That's all. Everyone, I need, there are 100 plus people. Yes. Clear to all this question. If this is clear, question is clear, all others are clear. इससे ज्यादा कुछ करना ही नहीं है इसमें. ठीक है. Perfect. चलो. If you are clear, give me the answer. So this is an open question now. Give me the answer for this. So you have 30 seconds. Everyone try it out. One person got B. Okay, let's do. देखिए, so a number density of a free electron in 3 dimension. 3 dimension means D is 3. I will not think anything. D is 3. It is increased 8 times. So number density is increased 8 times. So number of particles, number density, number of particles, always as I said, we will replace each other. So n dash is 8 times n. Fermi temperature. So you don't have to worry about Fermi temperature. If you know Fermi energy, Fermi temperature is also the same thing. You just need to multiply by Boltzmann constant. So think about Fermi energy only. So again, first of all, I need density of states. So density of states is e to power d by s minus 1. d by s. हाँ जी, s क्या होगा? 2. s2 क्यों होगा? Because they have said free particles के लिए s is always 2. We discuss the 2 special cases. S is 2 for free particles, right? So if s is 2, 3 by 2 minus 1 is e1 by 2. Then I use this formula again. Number of particles equals to 0 to ef ge into de. You put the value of ge is e की power 1 by 2 into de. You do the integration, you get e की power 3 by 2, right? Obviously you also have 3 by 2 in the denominator, but still, since we are only looking at the dependencies, constants we are not considering. So we put the value, so that gives you number of particles is directly proportional to ef की power 3 by 2. Hence ef is directly proportional to n की power 2 by 3. ठीक है. So ef dash by ef will be n dash by n की power 2 by 3. and that they have already given that number of particles has increased 8 times. Number density has increased 8 times. So this thing is 8. Okay, so 8 को I can write as 2 cube. So this 3 and 3 cancels, you get 2 square. 2 square is 4. Option A. Okay, perfect. Chalo, very good. Anyone has a doubt? All of you are clear, but anyone has a doubt? That is what I'm asking. First two questions clear as crystal clear. Okay, good. No one has doubt. चलो, इसका तो आंसर सभी को पता है. डायरेक्ट 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 बिना सोचे बताइए. राइट, बिना सोचे बताइए. ये तो फॉर्मूला ही आ गया सीधा. यस 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 यस. क्विक 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 एवरीवन. बी. चलो, कुछ नहीं करना. नथिंग नथिंग, नो सोल्यूशन. ये दिस इज अ 5 मार्क क्वेश्चन इन एन एग्जाम. ओके 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 ओके. चलो, नाउ let's read the question carefully. Question number 4. Consider a free. Okay, free जैसे ही word free सुनाई दिया, s is equals to 2. Fermion gas. Fermion means I have to use Fermi statistics in a hypercubic infinite potential well, hypothetical 4-dimensional space. Okay, D4. What will be the expression for ground state energy? What did I said? What did I said? Ground state हो तब भी क्या निकालेंगे? Even if it's a ground state, what will you find? Average. तो आपसे क्या पूछा है यहाँ पर? What they have asked you? Average energy per particle. Per particle means divide by n, divide by total n. ठीक है. So have I given you the formula for average energy? Yes. Have I given you the formula for total number of particles? Yes. Can you do both? Can you do both? And you have to give an answer in terms of Fermi energy. So what is the formula for total number of particles? 0 to EF, GE into DE. And what is the formula for average energy? 0 to EF, E into GE into DE. You can easily find GE. GE, how do you write? E की power D by S minus 1. D by S करेंगे तो क्या आ जाएगा? 4 by 2 is 2, 2 minus 1, 1. करो भाई, करो करो करो. Everyone get an answer. Give me correct answer. What is everyone getting
B,
for this? Yes, type it out your answer, everyone. B.
B.
Most of you are getting B. Yes. Yes. Very nice. Very nice. B you are getting. Anyone has a doubt in this? Doubt is in this, anyone? So कैसे करेंगे? एवरेज एनर्जी E into GE. E into E is E square. E square का integral E cube. E F cube by 3 is your average energy. Total number of particles comes out to be E F square by 2. All you need to do is divide both of them. If you do divide both of them, you get your answer B. Any doubt? Anyone has a doubt? Everyone is clear, but someone has a doubt. Please go ahead. Especially those who are doing this topic for the first time. Yeah. Right. यही टाइम है. If you ask doubt now, you will be saved. Yes. कोई doubt? Perfect. 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 Give me answer. Give me answer. Question 5. Question 5. Give me an answer. Pressure. Pressure. So pressure का formula भी तो है. So give me a look at it. Let's look at it. So what is the formula I gave you? Pressure is equals to S by D plus S. N into EF. This was the formula I gave you. What is non-relative? Free? Free. The moment I say free, S is 2. 3 dimension, D is 2. Okay. So in this case, how does Fermi energy depends upon N? We just did that. The same thing we did in the previous question, that my Fermi energy, so this question you remember, my Fermi energy depends upon N ki power 2 by 3. If your S is 2 and D is 3, you have already done this mathematics that your Fermi energy depends upon N to power 2 by 3. So that is all you need to do in this. So all you need to do is put N ki power 2 by 3. So your Fermi energy depends upon N ki power 2 by 3. There is already one N here. So N1 into N2 by 3 gives you N5 by 3. So how does your pressure depends upon N? N की power 5 by 3, which is your option number A. ठीक है. You already have this N. All you need to do is how does your Fermi energy depends upon N? Then you multiply both, you get answer A. ठीक है, डोंट वरी अबाउट दिस बिकॉज दे आर नॉट आस्किंग यू द कांस्टेंट आल्सो, दे आर ओनली आस्किंग यू द डिपेंडेंस, सो वी नीड टू वरी अबाउट दिस. एनी डाउट? एनी डाउट? Question 5, doubt. If you have a doubt, go on, go on. Clear. No, no one has a doubt. Question 6. Question 6. Difficult question. I need answer. Little difficult. Not very difficult. Small, little bit difficult. Question 6. So whenever energy is asked, what will you find? What will you find? Will you find Fermi energy or average energy? Tell me. They are asking you energy. What will you find? Average or Fermi? Average. In the very beginning, I said, whatever kind of energy they ask you, find average. So average energy. First of all, what is S? S is 1 because E is equals to PC. P को मैं क्या लिख सकता हूँ? H cut K. Perfect. S is 1. D is what? Dimension is 2 dimensional. D is 2. So density of states D by S. D by S करेंगे तो आ जाएगा 2 minus 1 E. अब I need to find an average energy. If I find average, first of all, I can find total number of particles. Total number of particles can be written as 0 to EF E into DE. I get EF square by 2. Okay. From here, I can say that my EF depends upon n की power 1 by 2. ठीक है, n की power 1 by 2. Now I need to find average energy. If I need to find average energy is E into GE into DE. So E is E. GE depends upon also E. I need to integrate this, so I get EF cube by 3. ठीक है. How does my Fermi energy depends upon particle? N की power 1 by 2. If I put n की power 1 by 2, I get n की power 3 by 2. So my actual answer is A. Why were people getting B? I don't know. B क्यों आ रहा था?
एवरेज एनर्जी
B क्यों
निकालने
आ
की
रहा था?
जगह हमने डायरेक्टली वो नंबर डेंसिटी से कर दिया तो
Sorry, क्या?
sir, instead of calculating average energy, we
हाँ.
recalculated directly the number density and compared it with the density. So that's why
Yes.
we are
No.
getting.
Wrong. Energy means average
Uh,
energy. No, not Fermi energy. Okay. Energy means तब भी तो B नहीं आना चाहिए. तब भी कैसे B आया? तब भी 1 by 2 आ रहा है ना? तब भी कैसे B आया? Right? B तो तब भी नहीं आना चाहिए. Right? ठीक है, ध्यान से सोच थोड़ा सा ना. देखो फॉर्मूला वही 3-4 लगने होते हैं. एवरी टाइम वी ओनली हैव टू अप्लाई 2-3 फॉर्मूला. तो मैं वही कह
sir,
रहा हूँ थोड़ा सा.
actually, what I thought na that since number density, since usually we used to take number by volume, so
मैं
instead of that
वही
we
गलतियां कर रहे हो ना. वही गलतियां किसने बोला सोचना है? लेक्चर्स का क्या मतलब? सोचना ही तो नहीं है पेपर में. यू हैव टू
rho
रिलेट.
is
मैं अगेन
simply
एंड
n we
अगेन
have
व्हाट आई एम
taken.
सेइंग, एवरीवन लिसन टू दिस केयरफुली. यू डोंट हैव टू थिंक इन एन एग्जाम, यू हैव टू रिलेट इन एन एग्जाम. whatever you know, you have to relate it with the question कि okay energy है तो I know average energy, I need to find average energy. N and capital N always are irreplaceable. So rho is a number of electrons per unit area. ये सब की चीजों को तो मैटर ही नहीं करता ना. Rho is a number of particle electrons. So N and capital N I will always replace with each other. Energy per unit area. ठीक है, मतलब बेसिकली क्या है कि एनर्जी की दोनों साइड बात आ रही है. अगर आप दोनों साइड एरिया डिवाइड कर देंगे तो वन साइड यू विल हैव एनर्जी पर यूनिट पार्ट एरिया एंड अदर साइड यू विल हैव नंबर ऑफ पार्टिकल्स पर यूनिट एरिया. तो पर यूनिट एरिया को यू डोंट हैव टू वरी अबाउट. सो एनर्जी दे आर आस्किंग मींस एवरेज एनर्जी. यस, एनीवन हैज अ डाउट? गो ऑन, गो ऑन, गो ऑन. पीके यू हैव डाउट? गो ऑन. Yes. But is it clear now? Is this question clear now? एनर्जी पर यूनिट हुआ तो एनर्जी डेंसिटी हुआ ना. तो हुआ एनर्जी डेंसिटी. मैं वही तो बोल रहा हूँ. नंबर ऑफ पार्टिकल्स पर यूनिट वॉल्यूम को मैं कैपिटल नंबर ऑफ पार्टिकल्स एंड नंबर ऑफ पार्टिकल्स पर यूनिट एरिया को मैं एक दूसरे से रिप्लेस कर रहा हूँ. सिमिलरली एनर्जी और एनर्जी पर यूनिट एरिया को भी मैं एक दूसरे से रिप्लेस कर रहा हूँ. बेसिकली डिपेंडेंस में पर यूनिट एरिया का क्या काम? लेट्स से एनर्जी डिपेंड्स अपॉन एन. दोनों साइड एरिया डिवाइड कर दूंगा तो एनर्जी पर यूनिट एरिया डिपेंड्स अपॉन नंबर ऑफ पार्टिकल्स पर यूनिट एरिया. Got it? So that is what I am telling you from the beginning. Okay? Yes. Don't worry about per unit volumes, per unit areas. उसकी वजह से question will never get affected. Okay? Cool, 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 cool. Okay. Question 7. Quickly. Again, गलती होगी. Mistake can happen. Very carefully do this. Give 1 minute to this question and correct answer should be there. Okay. Let's do it. Let's do it. Okay. So again, nothing. 3 dimension, non-interacting particles, K cube. So S is 3, D is 3. Density of states does not depend upon energy because D by S is 1. 1 minus 1 is 0. So density of states does not depend upon energy. But they're asking you pressure and energy. Average pressure to energy density. Basically, they're asking you the dependence of pressure divided by energy. Pressure का formula, pressure is given by S by D plus S into N into Fermi energy. ठीक है, S is what 3 by 6. So basically 3 by 6 is 3 by 6. N is N and EF is EF. ठीक है. So now we need to think first of all what is EF. How do we find EF? ठीक है. So let's do this. So in order to know EF, we always use total number of particles or small n or capital N you can replace anytime. 0 to EF, GE into DE. Now GE does not depend upon energy. Basically this is 1. So integration will be E. If you put limits, you will get EF. So basically N and EF are equal. Equal means dependence is equal. So you simply put EF ko N. Simply put EF ko N. So you get N square. So this is your pressure. Pressure is done. Now energy. Whenever they ask energy, energy does not mean Fermi energy they are not asking. They are asking you average energy. One thing I made it clear in the beginning. So average energy. So average energy is E into GE into DE. This is 1 because this does not depend upon energy this time. So integration of E will be EF square, E by square by 2. You put the limits, you get EF square by 2. EF and N are same thing. So I can say N square by 2. So pressure is also N square by 2. Average energy is also N square by 2. If you divide both of them, you get answer 1. So C will be correct answer. Yes, everyone? Yes. Yes. Clear? Disha, is it clear? Adyasha, Saishwar, all of you clear with this? Adyasha is not in the class today? Yes, Saishwar is here. Yes. Uh, okay, good. Yes, okay, good, good, good. Cool. Very good. Chalo. So these were all the questions which came from the Fermi statistics. Now can we go on to the boson statistics? Yes. Danji. So Fermi statistics का कोई भी question, any question under the sky comes, first 3-4 formulas are enough to solve. Okay. Now we go for Bose Einstein statistics. Bose Einstein statistics में most important is Bose Einstein condensate. Now what is Bose Einstein condensate? So basically Bose Einstein condensate is a transition. It's a phase transition. So when you have a low temperature, your de Broglie wavelength become very large. So de Broglie wavelength is given by, you remember, H by P. P can be written as 2m kBt. So basically de Broglie wavelength depends upon, inversely depend upon temperature. When the temperature gets lower and lower and lower and lower, de Broglie wavelength becomes larger and larger. So when the temperature is very low, the particles have a very large de Broglie wavelength. But the problem is that particles are confined in a very small space. Let's say inside a nucleus, there are many neutrons. Now, if there are many neutrons, they're closely spaced with each other. And if their wavelengths are very large, they will start overlapping with each other. Hence, what will happen is, instead every particle existing separately, all the wavelengths will superimpose with each other. So let's say there are million of particles and wavelength of each particle is very big, so that the wavelength of one particle overlaps with wavelength of other particle. Hence, all the particles ka wavelength jo hoga, waves, de Broglie waves, what will we call it, will overlap with each other. Hence, we will get a one big wave or superimposed wave. What happens when two waves superimpose? You get a third final wave. What will happen if millions of waves superimpose with each other? Now you will not have millions of separate waves. Now you will have one superimposed wave. It means all the particles got coupled to each other. So now all the particles are existing as one particle, like an army of people. So what is the difference between a normal citizens and an army? If you see thousands of normal citizens, everyone is doing their own. Someone is eating samosa, someone is going, someone is reading the book, someone is scrolling the memes, someone is talking on the phone. Everyone is having their own wavelength. But army, if you see the army walking, marching, everyone's hand is going up, down. So whatever one person is doing, everyone is doing the exact same. So although they are made up of 1,000 people, but these 1,000 army men are acting like a one big particle. This is what we call is a state of Bose Einstein condensate, without going in too much detail. So there comes a particular temperature, which we call it as critical temperature or a Bose Einstein temperature. At this temperature, if you are lower than this temperature, you have an army. And if you are above this temperature, you have a normal citizens. So this is a Bose Einstein condensate. This is a normal state. Okay. So at this particular temperature, this thing completely changes. And we are interested in this region. What are the parameters in this region? Parameters in this region means what is the pressure in this region, what is the entropy, what is an energy, what is the number of particles. All of the things which we answered for the Fermi Dirac, the same answers we needed for bosons as well. So now what we have is a bosons. So now give me 3 examples of Bose particles, everyone. What are the 3 Bose particles which are mostly used? Mostly used ones. First, pion is a wrong answer, but still. Three examples.
Gravitons and photons.
Okay, graviton. Okay, what else?
Photon.
Photon, very good. Yeah. Graviton, photon, and phonon.
Ions.
These are the 3 mostly used. Graviton
Ions.
also we don't use. Photon and phonons we don't very use, right? So photons and phonons are most used. Phonons are used in thermal vibrations, crystal vibrations. Photons are used in electromagnetism. Good.
Ions. Ions. Towns.
Okay, yeah, that is also right. Let's go on. So let's move to the important parameter. So now again, the same kind of table we need, the table we made for the Fermi Dirac, the same table we need for this. So for T less than TB, what are the parameters? Again, I'm starting from the same logic that my dispersion relation is that E is depending upon K ki power S. Every system has some dispersion relation. E ki power, E depends upon K to power S. Dimension is D. I have defined a simple term which is A equals to D by S. मतलब ये just simplification के लिए है. You can even keep on writing D by S. Does not matter. So you can define A as D by S, or you can simply write the formulas as D by S. Number 1, what is a condition that Bose Einstein condensate will occur? Not in every system Bose Einstein condensate is formed. The condition for Bose Einstein condensate is that D by S will be greater than 1. Okay. And which basically means that A will be greater than 1, because D by S I'm calling it as A. So D by S will be greater than 1. So keep on writing along as I'm explaining. So number 1 is, what is a condition that Bose Einstein condensate will occur? D by S is greater than 1. Number 1. Okay. How does how does Bose temperature or critical temperature depends upon number of particles? Either you call it as number of particles, or you can call it as number of particles per unit volume. Again and again I'm saying I can replace both of them because I am only looking for dependencies. So multiplying with the constant does not change anything. So how does TB depends upon N? 1 by A, which basically means not D by S, S by D. So the Bose temperature depends upon number of particles as S by D, which basically means if you have more particles, critical temperature will be something else. If you have less particle, critical temperatures will be something else. So critical temperature, where the transition happens, basically you go from a unsynced position to synced position, individualism to army. The temperature where you go like that also changes with number of particles. And how does it matter? S by D. Okay. Then another interesting formula, n naught by n. N is a total number of particles. N naught is a number of particles in this region. So understand like this. Think like this. Let's say your Bose temperature is 3 Kelvin, 3 degree Kelvin, and you have 1 million total number of particles. So N is 1 million. Now let's say you are reducing your temperature. So let's say you are reducing. So temperature you are reducing. You are at 3.2 Kelvin. All the particles are above. None of the particle is in Bose Einstein condensate. Once you reach lower temperature, let's say you reach 2.9, what do you think? All the particles will become Bose Einstein, or some particles will become Bose Einstein, and then slowly all the particles will become Bose Einstein? What do you think? All particles or some particles? Yes. Once you cross this boundary, will all the particles become Bose Einstein immediately, or only some particles initially become Bose Einstein?
I
Guess.
think initially it will become slow because suddenly I don't think so. It should go like that.
Yes, everyone guess. Some. So actually the answer is some.
Particles.
When you just cross, some particles, most of the particles are in Bose Einstein, but still some particles are not. Once you are very much away from here, let's say your temperature is 1 degree Kelvin, then all the particles basically becomes Bose Einstein. Okay? So n naught number of particles means how many particles are in the ground state. Ground state means how many particles are in Bose Einstein condensate. And total n means how many total number of particles are there. So their ratio is given by 1 minus T by TB की power A. A you know what is A? D by S. Okay. So first three formulas clear to all. What is the meaning of every term in
So is
first
it
three formulas?
total number of particles or the remaining number of particles? I think
No,
total number.
total. N is total. Okay. So this tells you what is the fraction of particles in Bose Einstein condensate. Yeah. Yes, first three formula clear to all. I don't need 2-3 answers only. Yes, everyone. N naught is the number of particles in Bose Einstein condensate. So let's say you cross. Total number of particles were n. N naught means how many particles are there in Bose Einstein condensate. So let's say out of 1 million, 0.8 million are now in Bose Einstein, and 0.2 million are still not in Bose Einstein. So that is the kind of situation. Okay, three formulas are clear. So let's go for fourth one. I hope you are writing it down. Energy density. Again, energy density, we will replace each other very frequently because you don't have to rush me like that. ठीक है? इससे तेज क्या पढ़ोगे? Don't worry. Relax करो. Energy density is U. So energy density and energy are completely replaceable because energy density means energy per unit volume. So again, the same thing. Dividing by volume, I'm not worrying too much about this because that is just a constant. And I'm constantly looking for dependencies. So energy density depends upon T ki power A plus 1. T ki power A plus 1. So one thing that you need to keep in mind, in most of the questions of Bose-Einstein condensate, either they will be asking you the dependence on N or they will be asking you the dependence upon temperature. In 90% of the case, they will be asking you the dependence upon temperature. Okay? So that thing you can keep in mind. So how does energy density depends upon temperature? T ki power A plus 1. A is what? D by S plus 1. Then how does pressure? Now the formula for pressure is not S by S plus D into N into EF. This was the formula for Fermi Dirac. What is the formula for pressure now? S by D into energy density. S by D into energy density. ठीक है? KB तो लिख लो, नहीं लिखो, नहीं भी लिखो, ऐसे ही लिखा है यार, इतना don't take this too seriously. KB is just a constant. लिखना है लिख लो, नहीं लिखना है मत लिखो. We only need temperature. ठीक है? KB तो होगा ही ना, constant तो यहाँ पे there will be so many constant. मैंने कुछ भी नहीं लिखवाया आपको, right? We are only looking at dependencies. If you look at the exact formula, there will be so many other constants also here. Okay, we are not worried about that. So pressure is given by S by D into U. Okay, so yes, that's all. So whatever is the dependence on U, the same is the dependence on pressure, because pressure is directly proportional to U. This is simply a constant, right? So pressure is directly proportional to U. But keep in mind, they can even ask you the exact equation. That is why I have given the exact equation for pressure, that pressure is given by S by D into U. Okay. Then comes entropy. Entropy depends upon T to power A. ठीक है? I think this is not entropy. This is specific heat. Specific heat depends upon T to power A. And I think, yes, entropy also depends upon T to power A. ठीक है? Both of them are true. ठीक है? Entropy also depends upon T to power A. A, you know, is what? D by S. Okay. So how does specific heat depends upon T ki power A? Because if energy is depending upon T ki power, let's say energy depends upon T square, then you know specific heat is given by differentiation, right? So it will depend upon T, right? So if energy depends upon T ki power A plus 1, then specific heat will be depending upon T ki power A, because you do differentiation with terms of temperature. Okay. And the last of this is chemical potential. For ideal boson system, so if your system is ideal boson system, the chemical potential will always be 0. Okay. So please note all of these down, 4 formulas, then we will talk more. Once you are done, please let everyone clear with these all formulas, basic formulas, right? Now these formulas were for the dependencies, but one special case we also need. Okay. In that one special case, we need the exact formulas also. Not only the dependencies, but we also need the exact formula. And that special case is S is equals to 2 and D equals to 3, which basically means free particles in 3 dimension. Because once it is free, it is given free chemical potential for fermion is like asking a very, very random question. So chemical potential in fermion is not a very important thing. So what Fermi energy do in Fermi statistics, chemical potential do that in boson. So that is why you see most of the answers in Fermi Dirac was in terms of Fermi energy. So for जो काम Fermi energy का है in Fermi Dirac, the same काम is chemical potential in case of बोसोन. ठीक है, इसके ऊपर हम बहुत डिटेल में भी बात कर सकते हैं, बट ये समझ के चलो. That is why in Fermi Dirac we don't define chemical potential, we define Fermi energy. Okay, चलो. Now number 1, in this case what will be the total energy? So only one or two formula you need to keep in mind. Number 1 this and number 2 this. First of all of you tell me, is this dependence correct? According to the dependence formula you learned, is this dependence correct? Yeah. How does energy depends upon T? D by S plus 1. A plus 1 होता है ना? What is D in this case? 3 by 2 plus 1. What does it? T की power 5 by 2. So isn't this dependence correct? What do you say? देखो जरा. Energy density depends upon T की power A plus 1. A is what? D by S. If you do D by S, what do you get? 3 by 2. 3 by 2 plus 1 is what? 5 by 2. So all of you can see that this dependence is correct. Yes? So total energy ka formula is given by 0.77 nkb. N is the total number of particles. Kb, temperature ki power 5 by 2 divided by Tb ki power 3 by 2. Okay. So this is a formula for your energy in case of this very special case in which S is 2 and D is 3, which basically means free particles in 3 dimensions. Then we do specific heat. Specific heat, what do? You just differentiate this with temperature. If you do differentiate this, 5 by 2 will come here. So if you multiply 5 by 2 with this, you get 1.93. nkb remains nkb. This remains as such because this is a constant. T ki power 5 by 2 becomes T ki power 3 by 2. Okay? So t की power 3/2. That is your answer. This was simple. If you remember first formula, second is direct. The third is very important. Third is very important. Third is what is a Bose temperature. So Bose temperature is given by 2 pi h bar square divided by mkb n by 2.612 की power 2/3. Is this dependence right? What do you say? Look at the first formula. Is this dependence right? Second
Yes,
formula.
sir.
Yes. Because you remember I said TB depends upon n की power 1 by a, or you can say s by d. S by d is 2/3. ठीक है? So interesting fact here is that TB depends inversely on mass and TB depends directly on n की power 2/3. These are the two more important things, but exact formula also you should keep in mind only for this special case. So if all of you are here clear with it, Rohini changes with dispersion relation, right? So dispersion relation is given k की power s, right? So in that case, according to dispersion relation, s changes. So all of you clear with the formulas? Can we move on to the numericals now? What do you say? Yeah, current numericals. Let's do first question. So let's do one question I will help you with, and then other questions we will do as a practice. The excitation of three-dimensional solid are bosonic in nature. So you see now I need to use boson. Three dimension means D is 3. Perfectly fine. I know D is 3. Dispersion relation is given. Omega is directly proportional to K square. So S is 2. Okay. If the chemical potential is 0. Chemical potential 0 means you are in ideal boson nature. That is the only meaning to write this line. This line only telling you that you need to apply Bose statistics. What is the behavior of specific heat? Batao bhai, very quickly. Tell me, how does specific heat depends upon temperature?
D by S.
Yes. Quick. T की पावर D by S. महक जल्दी करो. अब प्रेशर में गलती नहीं करना है. D by S. क्या करेंगे D by S में? Good. So D by S will be 3/2. क्या आंसर आ गया भाई? C. कुछ भी नहीं किया. 5 मार्क्स फ्री में लेकर चले गए. गुड, वेरी गुड. चलो नेक्स्ट क्वेश्चन. Bose condensation occurs in liquid helium. Okay. At 2.17 Kelvin. So sort of Bose temperature is given to me as 2.17 Kelvin. At what temperature Bose condensation will occur for the same helium if the density of states is 1000 times smaller? So what I have done is now I have made my density of states 1000 times smaller. Give me the answer. It's perfect. So what have we do? Which formula we apply? How does Bose Einstein temperature depends upon n? We just did 1 by a. 1 by a means s by d. S is what? 2. Okay? If it is not given, obviously you take a conventional case, right? Simple case. If the dispersion relation is not given, the special case that you studied, we will take that only. D is 3. Okay? So it means n depends upon 2/3. Then I just need to do TB dash by TB, which means n dash by n की power 2/3. N dash by n is 1/1000 because density has decreased by 1000. So 1/1000. 1/1000. 1000 can be written as 10 की power 3. This 3 and this 3 cancel, so you get 1/10 का square. 1/10 का square is 100. So basically your temperature decreased by 100. So if your temperature decreased by 100, so if you, this was your initial temperature, so 2.17 को if you divide by 100, ठीक है, you can write it as 21/7 divided by 1000. 1/1000 is known as millikelvin, so that is why your answer number B is correct. Anyone has a doubt in this question? Yes, you can go on. Very good, everyone clear with it. Next question, let's solve it out. Okay, सीधा आंसर दो, सीधा सीधा, कुछ सॉल्व नहीं है इसमें. क्विकेस्ट जल्दी जल्दी जल्दी. सी 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 सी. What is the condition for Bose Einstein condensate to occur? D by S has to be greater than 1. चलो बढ़ गए आगे. Next. चलो next question. Next question. You need little bit of caution here. So cautious you have to be. A gas of photons. The moment you hear the word photons, can you tell me S? What will be the value of S? 1. Why? Because you remember in the initial, when I was teaching you Fermi Dirac Statistics, I told you if it is a massless particle. For massless particle, energy is given by Pc. P can be written as h cut k. Hence, E is directly proportional to k. Relativistic वगैरह की नहीं सोचना है सर. No relativistic here. It's a massless particle. Okay. It is, that is why it is relativistic भी बोल सकते हैं. Yes, that is also true. So S is equals to 1. So S is 1. Obviously, in this question, it is not given, but since they are saying volume, so dimension is always obviously equals to 3. So can you tell me how does pressure depends upon temperature? How does pressure depend upon temperature? अरे आंसर मन में करना है. What is pressure? Temperature. So what is the formula for pressure? Formula for pressure is S by D depend upon U, right? S by D on U. So as I already told you, however the energy density changes, the pressure changes in the same way. And how does energy density changes? Energy density changes by U ki power A, sorry, T ki power A plus 1. What is A? A is D by S, right? D by S, that is 3. So 3 plus 1 is 4. So your energy density depends upon temperature ki power 4. So pressure also depends upon temperature ki power 4. So if you double the temperature, your pressure will become 4 times. 2 ki power 4 is 16. B answer done. Okay. Any doubt, anyone? 5 mark question. More than 1 minute you don't need. Okay. Perfectly fine. Any doubt? Any doubt here? Good. Okay. Give me an answer then. Give me an answer then. Similar question. Very quick. Very quick. So black body radiation. Black body radiation will also be a photon. Right? Black body radiation will also be a photon, right? C and D. Some people getting C, some people getting D. Disha has said D, C, both. Chalo.
No, sir, actually, I was typing C.
Okay. C. Chalo. देखो यार simple है. How does, so they are asking for entropy, not pressure here. So entropy depends upon T ki power A. A is what? D by S. Dimension is 3, S is 1. Right? S is 1. Because again you are in photons. Black body radiation is a photon. In photon, S is 1. So A is 3. So A is 3. So entropy also depends upon 3. So if you double the temperature, 2 की power cube will be 8. Whoever is getting 16, I don't know how you are getting 16. ठीक है? सिंपल है यार. सारा तो बताया. अब तो गलती कोई, there is no margin of error now. ठीक है? महक क्या कर रहे हैं आप? गलत कर रहे हो. राज भी गलत कर रहा है. विक्टस इज ऑल्सो डूइंग रॉन्ग. ये सब नहीं करना है. ठीक है? सोचो. सॉरी कोई बात नहीं बच्चे. सॉरी बोलना है. चलो नेक्स्ट. दिस क्वेश्चन. कंसीडर अ ब्लैक बॉडी रेडिएशन. ब्लैक बॉडी रेडिएशन का मतलब है फोटोन. फोटोन का मतलब है S1. परफेक्ट. 2-dimensional बॉक्स D2. हाउ डज एनर्जी डेंसिटी डिपेंड्स अपॉन टेम्परेचर? हो गया भाई. कर दे भाई, जल्दी कर दे. रितिका क्या हो गया? सी कहां से आ गया? रितिका सी नहीं आना चाहिए. देखो, एनर्जी डेंसिटी डिपेंड्स अपॉन डी बाई एस. रितिका आई नीड करेक्ट आंसर फ्रॉम यू अगेन. डी बाई एस माइनस 1. तो डी बाई एस करेंगे तो क्या आएगा? हाउ विल यू डू डी बाई एस? सर डी क्या है आपका? 2. by s plus 1, sorry, d by s plus 1, 2 by 1 plus 1, it is u, sorry, t की power cube. ठीक है, आंसर नंबर ए. वेरी गुड, वेरी गुड. ओके, क्वेश्चन नंबर 7 इज एक्चुअली नॉट ट्रिकी, सिंपल. देखो, a system of non-relativistic non-interacting boson of mass m in two dimension, okay, d is 2, non-relativistic if they do not mention the dispersion relation, and if it is not photons, s will be 2, right? It's if it were photons, I would have taken s1, but they are normal bosons. It means they are free bosons. Basically, free bosons means s2. At what temperature Bose Einstein condensate occur? They are asking for the exact temperature. They are not asking for dependence. If I do dependence, so before I do dependence, I have to see whether Bose Einstein condensate can be formed or not. So for Bose Einstein condensate, d by s has to be 1. In this case, is d by s greater than 1? Is d by s greater than 1? No. So Bose Einstein condensate does not form. Bose Einstein condensate does not form means critical temperature is 0 Kelvin, because you can never reach 0. So if you can never reach 0, Bose Einstein condensate will never be formed. So answer number 4 is correct. Okay. So it was not direct asked, but it was indirectly could have been answered very simply. Okay. Any doubt in this question? Question number 7. Okay. Question number 8 is not difficult, but little bit someone can make mistake in D8. So listen to this question very carefully. So Bose condensation experiment is carried out on 2 samples. So you have 2 samples. Ideal Bose gas is there. So number of particle or number density of 1 is given and number density of sample 2 is given. How does pressures change? How does pressure change? So if you see the pressure, if you remember the pressure was what? Pressure was S by D into U. Okay. U. And you remember is, if you use the exact formula, you don't have to, but if you use it, S by D, S is what? S is 2, D is 3. If the system is not given, you always assume conventional system. Okay, conventional system. So let's see that. S by D, so it is 2 by 3 into U. You know the formula for U. So 2 by 3 into 0.77. I will use the exact formula now. So that is why I also gave you the exact formulas for one conventional system, because sometimes they ask you this also. This is your formula. Okay? Pressure is this. But they are not asking you the pressure as a function of temperature. No, they are asking you pressure as a function of number of particles. So one is that pressure depends upon N. Is it true, or I have to consider something else also? Is pressure only depending on N, or there is N hidden somewhere else also? Yes. Do you all agree that in TB also N is hidden? In the very first formula, you know, TB depends upon N की power 1 by A, which is S by D. S by D क्या होगा sir? S by D will be 2 by 3. ठीक है, right? 2 by 3, right? Perfect. It means here also we have N. So pressure not only depends upon N on this N, but it also depends here. So how does TB depends upon N? N की power 2 by 3, and there is 3 by 2 also. So 2 by 3 and 3 by 2 cancel, so you get 1. It means pressure does not depend upon number of particles. If pressure does not depend upon number of particles, then the ratio of pressure will be 1. So in this question, what I had to do was use the exact formula. And the exact formula I have given you, and they will not ask you exact formula for all. They will ask you the exact formula only for this conventional case in which S is 2 and D is 3. In that case, the pressure formula is basically S by D equals to U, and energy formula I have given you, and this is your energy formula. You can clearly see it depends upon N and TB. So this N I have written as such, and TB depends upon N की power 2 by 3. 2 by 3 and 3 by 2 cancels, it gives you 1. N by N gives you 1. Pressure does not depend upon number of particles. Yes, question clear to all? Success? Success khatam? Everyone, any doubt in this? So this was all about quantum statistical mechanics. That's all from my side. So before I end the class, let me give you the homework. Okay? So I will provide you only one notes, which is on microstates. How do you calculate the number of microstates? You must have seen the question that infinite well is there, you have energy levels, and you are putting particles in it. In how many ways you can put the particles, what will be the ground state energy, so on and so forth. So that is basically known as microstates kind of question, calculating the number of ways of doing the things in statistical mechanics. So I will provide the notes for it. Second thing that I will provide is last 5 papers. 2 questions. Number 1, Fermi Dirac questions and microstates questions. Okay? So this you will understand once you have read these notes, and Fermi Dirac questions already I have given you everything you need to know. So in last 5 papers, what are the questions which are asked from Fermi Dirac? Bose questions I already covered. So in last 5 years, whatever Bose questions came, I covered it. Fermi Dirac questions I have not covered it. I have kept it for you. I think one question I covered it, but other I have kept. So you try that questions. Also you try the microstates questions. Okay? So if you do not understand microstates in detail, even if you look at my solutions very carefully, you will understand how these questions has to be done. Okay? So that is going to be your homework. This is actually IIT JAM level syllabus. So that is why I'm giving you as a homework. So that is about today's class. Yes, मजा आया भाई. Everyone understood. बड़ा topic cover किया.